Good morning. This is the video recording of our presentation for the design and the implementation of our Ti-ADC 2014 project called Low Cost Battery Management and Data Acquisition System for Portable Electronics.
This is the circuit that we are using to measure the current and voltage to be taken as inputs to the buck converter. This will be used in two places in the block diagram. One is between the buck converter and the laptop, and the second between the laptop and the battery. This is the circuit diagram. You have your inputs here, 1 and 2, positive and negative inputs, and positive and negative outputs here. To calculate the current that is flowing through the circuit, we have a current sensing resistor RS. Now we don't want to use a fixed resistor RS, but instead plan to use a potentiometer because MSP 430 does not support floating point arithmetic. Hence, if we have a part as RS, we can calibrate RS so that the current that is flowing through this is VC, the potential difference across RS, into 2 power n. So that makes the number handling easy, since it's just right shifting by n slots. Yeah, so we'll have in the block diagram we'll have this at 4 places. This is your power in supply, followed by your measurement, followed by the buck converter. This goes to the laptop internal. From here it goes to the battery. So there's another measurement unit here, measure and battery. Now we need to measure the voltage and current at this point, and only the voltage at this point. We do not need the current there, but still, since we are designing a circuit, we might as well have a common circuit. So we'll have 3 inputs, which is basically I out, V out, and V. This will control the buck converter. This is a setup of the current measurement and logging circuit. We have a 40 volt AC adapter providing power here. It passes through a bridge rectifier and then a LM7832. We are using a IN333 instrumentation amplifier. Now we are using the 32 volt supply because the laptop the power supply input will be about 19 to 20 volts. The laptop battery has to measure about 11.1 volts, which means the bias has to be greater than 20 volts. So we are using a 32 volt supply. Since the current drawn by the amplifier is very little, we are just using a simple 100 microfarad capacitor. And then we have the LM32 is here, and then you have the instrumentation amplifier. For measuring the voltage is taken in, passed through the instrumentation amplifier, it is stepped down a little, and then this is a calibrating resistor for the instrumentation amplifier. Since it's built for measurements, a single resistor is enough to calibrate the output or the input ratio. Now the second one is the current is measured using a current sensing resistor. We used a potentiometer so that we can calibrate it, so that the multiplication or division factor to get the current from the voltage across this resistor will be 2 power n, where n is some integer. It could be 2 power minus n or 2 power plus n. So yeah, you can calibrate it using this. And we have also used a 10 watt pot, so that the heat dissipation in this component is very fast. It's built to dissipate 10 watts. So any voltage, so less power can be dissipated without much heating. This is the MSP FRAM board. We are taking in 2 channels right now. There are 2 more pins available, but then to access them we will need to redesign the PCB layout, because it's right underneath the PCB. One of them is the output of the instrumentation op-amp, which goes there, and then the second one is the voltage across the resistor, which comes here. Now what happens is
these voltages right now are being transmitted to the computer via the C3000 module. This is the C3000 module, the antenna, and then there is connected to the Wi-Fi hosted on this. You can see the values being read out. We are getting a very small voltage, because since the op-amp is since there is no input here, the op-amp output is floating for very small values. That's here. And current, since it's grounded, we are getting a constant 0. Discharge cycles and SOCs haven't been calibrated yet, so we still have 0 and 0. So if you keep running, if you keep this program, if you keep the hardware running across the battery for a long time, it will, as you charge it, you can see SOC rising, and discharge will update itself. Discharge cycle will update itself. This is the inputs for the second set of this thing. This comes between the this comes between the buck converter and the laptop. This is used to get your voltage, and this is used to get the voltage input between the laptop battery and the laptop itself. The current again will be measured using a similar statement. Okay, this is